Hello everyone. For today's lesson, we are going to learn about sustainable building ventilation systems. Before we start our lesson today, first I would like to tell you about the learning objectives of this class, specifically this lesson about sustainable building ventilation systems. First, we will understand sustainable ventilation systems in buildings, which there are three types: wind ventilation system, stack ventilation system, night purge ventilation system, and also we will study about other sustainable ventilation system available out there. Before we continue with our lesson, I would like to give a few questions as a pretest. The first question is, what is ventilation in buildings? And the second is, why is it important to have proper ventilation in buildings? Please answer according to your own understanding. First, we will learn about wind ventilation system. When placing ventilation openings, you are placing inlets and outlets to optimize the path air flows through the building. Windows or vents placed on opposite sides of the building give natural breeze a pathway through the structure. This is called cross ventilation. Cross ventilation is generally the most effective form of wind ventilation. If you look at the diagram on the presentation, you will see there are three images on the top row. The first image depicts single opening, the second, two openings on the same wall, and the third one, two openings with wings. The single opening is not a good representation of cross ventilation because there is only one inlet and one outlet, which is the same. The second one, two openings on the same wall, although have an inlet and an outlet that are separated, but they are still positioned on the same wall. This does not allow proper airflow through the room. And the third one, there are two openings with wings. This is a similar case as the second one, so this one is also not a good representation of cross ventilation. Now, if you take a look at the two images on the bottom row, these are depictions of proper cross ventilation systems. The first one, the inlet, the position of the inlet and the position of the outlet are on separate walls, in this case on adjacent walls. On the second image, you will see that the two openings are on opposite walls. Now, these two depict proper cross ventilation. Now, what happens if we look at it vertically? Placing inlets low in the room and outlets high in the room can cool spaces more effectively because they leverage the natural convection of air. Cooler air sinks lower while hot air rises. Therefore, locating the opening down low helps push cooler air through the space, while locating the exhaust up high helps pull warmer air out of the space. Now, this is based on the principle that cold air drops down while hot air rises. So by placing the openings vertically according to their purposes, we can manipulate the airflow within the room. Now I would like to explain a little bit about wing walls. Wing walls project outward next to a window so that even a slight breeze against the wall creates a high pressure zone on one side and low on the other. The pressure differential draws outdoor air in through one open window and out the adjacent one. Wing walls are especially effective on sites with low outdoor air velocity and variable wind directions. In this slide, you will see a diagram showing how we can apply this in building or architecture. Next, I would like to explain about stack ventilation system. Openings located low and high and on opposite sides of a space create a stack effect. Warm indoor air rising out through the high openings, drawing in cooler outdoor air through low openings. Using the air's buoyancy resulting from a difference in its temperature, climates with a minimum of 1.7 degrees Celsius, for example, with the difference between indoor and outdoor temperatures, the stack effect in a space or within a ventilation shaft will induce an air current that removes hot air from a space or building. The proper guidelines for locating inlet and outlet openings in a stack ventilation system is first, for residential spaces, a minimum of 3 meters apart in height, and for commercial spaces, a minimum of 4.6 meters apart in height. Now let's go through step by step for how we can apply or design a stack ventilation system in buildings. If you look at the image on the presentation slide, you can see that A indicates or shows the inlet opening positioned normally around 0.76 meters to 1.37 meters from floor level. This height is basically the average height of a human torso. B1 on the image indicates the shaft intake opening. This should be positioned as high as possible inside the room and can be positioned vertically on the wall or horizontally on the ceiling. Now, in the next slide, B2 shows the shaft outlet opening. This should be positioned as high as possible inside the shaft on the exterior wall, opposite from the intake opening. The inlet height should result in a path to allow appropriate ventilation for occupants' upper bodies. Now, in this image, you can see that the shaft height itself is determined by the amount of air distributed from the space. The larger the volume of the space, the higher the shaft. Okay, so how can we determine the area of openings within a stack ventilation system? Step 1, we must first find the building classification itself. For example, we need to know whether that building is classified as a residential or commercial building. Let's look at the residential building classification. Using the standard of the summer dry bulb design temperature, we can categorize the residential building into a warm, hot, or very hot location. Now, if the building is located around in an area or in a location that has an average temperature of 29 degrees Celsius, it will be classified as low. If it's 32 degrees Celsius, it will be classified as medium, and if it's 35 degrees Celsius, it will be classified as high. So we must pay attention to the average temperature of the location of that building. With commercial buildings, it's slightly different, because now we are looking not only at the temperature of the location of the building, but also its internal space heat gain. Now, if the space heat gain of a building that's located in a warm temperature is small, then that building classification is low. But if the internal space heat gain of that building is large, then it's classified as medium. You can see this on the table indicated on the slide. Now, step 2, we must determine the inlet opening areas. This is a diagram that we can use as a baseline to indicate or measure the size of the inlet opening. If you look at the diagram, you can see that the blue S-curve indicates commercial buildings, while the yellow S-curve indicates residentials. And within each curve, there is a dotted line in the middle. Now, this is to show if the building classification is high or low. The right line from the middle dotted line means that it's classified as high, while the left line from the middle dotted line classifies the building as low. So how do we determine the size of the inlet openings based on this diagram? First, we must design the size or the height of the shaft itself. For example, if the height of the shaft is 6 meters, then we must draw a straight line from the height indicated on the vertical diagram straight towards the S-curve. Now, if we are designing a building that is commercial, we must take that straight line until it hits the commercial S-curve, and then from there we can take a straight line vertically down to show how many percent of the floor area should be the size of the inlet openings. For in this case, it shows that for a 6-meter height shaft, we would need the size of the inlet opening to be 6.8% of the floor area of that room that is served. Now, after that, the next step is we must determine the size of the remaining openings. The area of the openings is directly related to the area of the inlet openings. Once you have determined the size of the inlet openings, you can determine the size of the other openings. In this diagram, the inlet is indicated as A, and the intake area of the shaft is indicated as B1, and the shaft outlet area is indicated as B2. The area of the shaft intake opening, B1, and the cross-sectional area of the ventilation shaft should be the same size as the area of the inlet openings, A. The shaft outlet opening, B2, should be the same size or bigger than the inlet openings. The larger the ratio between the size of the outlet and inlet openings, the greater the pressure difference and the more cool air that can be pulled into the space. So this is basically how an architect can manipulate the flow of wind by creating or calculating the size of the inlets and outlets of the shaft. Another ventilation system that is sustainable in buildings is called the night purge ventilation system. Now, the night purge ventilation system, also known as night flushing, is a passive ventilation system that utilizes a building's ability to detain thermal mass during the day and having open ventilation during the night to flush out the warmth absorbed by the building mass. This type of ventilation system works best in regions that have a high significant day to night temperature difference, where daytime air is too hot for natural ventilation and nighttime temperature is much cooler. This system requires building construction to have exposed mass, such as exposed concrete floor slabs, exposed brick walls, no carpets, no suspended ceilings, and so on. Thermal mass for nighttime cooling is most efficient in horizontal surfaces, in particular for floors, as cool ventilation air will tend to fall to the floor level. Now, as I mentioned, this type of system cannot be applied in just anywhere around the world. This ventilation system works best in areas that have a significant day-to-night temperature difference. For example, in desert regions. As we know, in desert regions, during the daytime, it can be very hot, while during the nighttime, it can be very cool. So night purge ventilation system works best in these environments. You can see on the slide there is a diagram or picture showing how this system works. During the daytime, heat gained from the outside temperature is absorbed through thermal mass. This means that the building must be made with materials that have good thermal mass absorption rate. Now, during the nighttime, the heat that is contained within the building's walls or floors or any other surfaces that have good thermal mass will be released, and then the cool air during the nighttime will absorb the heat that is released and will flush it out into the outside area. However, there are some limitations to night purge system. First, we must look at the climate, as I mentioned before. This system is only suitable for climates with a relatively large temperature range from day to night, preferably below 20 degrees Celsius at night. It is also not recommended for residential buildings or night occupancy, and its location should have adequate wind at night to provide cooling. The second limitation is in terms of usability. Usability concern where closing and opening of all openings every day can be tiresome. However, can be solved through mechanized windows or ventilation. With having windows open at night, there is a possibility of rain coming in. This can be solved with having overhangs or roofs with steep angles. And the third limitation of this system is in terms of security. Security can be a concern, especially in buildings that are unoccupied at night. Countermeasures with adequate security structures such as bars or screens. Exposed mass can also cause acoustic issues. Now let's look at a case study that applies night purge ventilation system in its building design. This is a secondary school in Burkina Faso in Africa. To get a more deeper understanding of the system of the night purge ventilation system, let's take a look at this video.
In 1991, architect Mick Pierce had a problem. An investment group in Harare, Zimbabwe, hired him to design the largest office and retail building in the country. But they didn't want to pay for the expensive air conditioning needed to cool such a large building. So that left Pierce with a seemingly impossible challenge. How do you design a building that cools itself? This is a termite mound. Millions of termites live inside these structures, some of which stretch an astonishing 30 feet high. Although these termite skyscrapers may look solid from the outside, they are actually covered in tiny holes that allow air to pass through freely. Like a giant lung, the structure inhales and exhales as temperatures rise and fall throughout the day. This termite ventilation inspired Pierce to use an approach known as biomimicry, imitating the ingenuity found in nature to solve human problems. Meet the Eastgate Center. The building is made from concrete slabs and brick. Just like the soil inside a termite mound, these materials have a high thermal mass, which means they can absorb a lot of heat without really changing temperature. The exterior of the building is prickly, like a cactus. By increasing the amount of surface area, heat loss is improved at night while heat gain is reduced during the day. Inside the building, low-power fans pull in cool night air from outside and disperse it throughout the 7 floors. The concrete blocks absorb the cold, insulating the building and chilling the circulating air. When the morning comes and temperatures rise, warm air is vented up through the ceiling and released by the chimneys. Thanks to this innovative design, temperatures inside stay at a comfortable 82 degrees during the day and 57 degrees at night. Not to mention, it uses up to 35% less energy than similar buildings in Zimbabwe. Since opening its doors in 1996, Mick Pierce's 90% natural climate control system has made the Eastgate Center a global landmark for sustainability. So, we must ask ourselves, if an architect could design a self-cooling building with termite-inspired climate control, what other innovations could Mother Nature inspire if we just paid closer attention?
Okay, so that was the video showing how a night purge ventilation system can be applied in buildings. Next, let's look at other sustainable ventilation systems out there. First, let's look at the HVLS, or known as high volume, low speed ceiling fans. Now, this system is more of a man-made system because with ceiling fans, we are applying human technology into the building design. So what is HVLS fan? HVLS ceiling fans are fans that rely on their size to distribute large volumes of air downward. HVLS fans produce columns of air which flow down and horizontally along the floor until the column hits a side wall or another fan that carries it further. Physically, HVLS are larger in diameter than regular ceiling fans and have long, thin blades. To get a deeper understanding of how HVLS system or fans work, let's take a look at this video.
Every time they turn, they save your facility more money.
I thought actually they gave us the wrong bill. I thought somehow, well, it can't be, it's got to be more than that.
High volume, low speed, or HVLS fans are starting to become an energy-saving staple in industrial, commercial, and residential spaces. They are growing to become a major player in the energy-efficient green movement. HVLS fans are ceiling fans that are greater than 7 feet in diameter. Unlike the personal fans you use at home, HVLS fans rely on their size, not speed, to move a large amount of air. HVLS fans produce columns of air which flow down and horizontally along the floor until the column hits a sidewall or another fan that carries it further.
We had a couple employees say, "Thank you for turning the heat up." We hadn't turned the heat up. All we did is move the air around. That was brilliant.
Small business owner Rick Krug saw the money-saving power of HVLS fans firsthand. He owned a restoration service in northern Arizona where it can be extremely cold in the winter. Crew kept his trucks in a large building.
And it was heated by gas radiating heaters. So it was very inefficient, but it did heat the building. Just cost us a lot of money.
Normally, you would think of fans as cooling appliances during the summer, but actually, HVLS fans are extremely effective in the winter. Through a process called destratification, HVLS fans mix warmer ceiling air with the cooler air at the floor to create an even temperature throughout the space. This method can cut your electricity bill by a huge percentage.
It moved the heat throughout the entire building evenly, so it wasn't just coming down on something. Saved us a bundle. I think our heating costs went down at least a fourth, sometimes a half, depending on how cold it was outside, simply by moving the air around efficiently.
As for the summer, the fans are able to make the feel-like temperature much lower than the actual temperature in the building, thus allowing the business owner to use less energy to cool the area down. The applications are endless. For example, in the agricultural industry, HVLS fans can reduce food spoilage, keep animals healthier and happier, and even keep the bug smells away. Or in manufacturing and warehouse settings, temperature is a key part of worker comfortability and thus productivity. HVLS fans help you reduce costs and keep your workers happy. In the food and beverage industry, fans maintain the temperature, thus ensuring quality control. On top of that, HVLS fans reduce condensation on floors, prevent metal from rusting due to that condensation, and can discourage birds from perching and nesting in facilities where doors are kept open.
I would recommend it to any building or any business that wants to answer their problem without a huge cost.
Okay, so what are the benefits of HVLS fans? Well, first, it helps improve air circulation and protect occupants' health. Second, it increases productivity and safer working conditions. Third, it helps reach energy efficiency goals. Fourth, it helps even out the temperature in a building during winter, sustainably cutting down heating costs. Fifth, it cost effective in operation. And sixth, it has dozens of applications for nearly every industry out there. So what are the differences between HVLS fan and regular ceiling fan? With HVLS fans, they move large volumes of air effectively. They produce slow-moving columns of air that don't kick up allergens and irritating dust and debris. They move quietly and don't disrupt employees. And they're larger blades that generate large columns of air that can reach more space. While with regular ceiling fans, they are choppy and ineffective of moving air around. They are quick-moving blades that kick up unwanted materials. They make loud buffering and humming noises that can be bothersome to occupants. And they have short blades that don't have a far reach. So those are the systems, the sustainable ventilation systems that can be applied in building or in architecture design. Now we will have a post-test. First, describe what is wind ventilation, stack ventilation, and night purge ventilation system. Second, explain briefly how you can apply one of the ventilation systems described in this lesson. And please, again, answer according to your own understanding. Okay, everyone, that's the end of this lesson. I hope everyone now has a deeper, more comprehensive understanding of how ventilation system works in buildings and what sustainable ventilation systems there are that can be applied. I will see you again in our next lesson. Thank you and goodbye.